Welcome to this discussion. We're going to go a little bit further now. We've talked qualitatively about different methods and so on for finding heat transfer coefficient. We're going to go into a little bit more detail now and start looking at how we can come up with actual models. So there are 5 basic methods that have been used in the past for this process. The first one is exact solution of the boundary equations. Now the existing equations are only complete for laminar flows, and the solution is still quite complicated and requires numerical solution of the balance equations. In spite of this, we have some solutions for simple systems like a flat plate, an airfoil, a cylinder, and so on. And these models are useful because they can be a basis for checking the validity of other methods. Now, we can also use approximate solution of the boundary equations. We use assumptions to solve a plausible but much simpler equation like the carbon momentum integral. This allows us to obtain solutions to problems we can't solve exactly, like turbulent flows. They're not perfect solutions, but they allow us to come up with an answer within what we call engineering accuracy. It's accurate enough that we can make a decision based on the result. We also have the momentum heat transfer analogy, which we talked about during dimensional analysis. It's a useful tool. We come up with simplified models that allow for solutions using statistical theories. It is practical, it's reasonably accurate, but it may not be theoretically sound. We can also look at dimensional analysis and experiments. Mathematically, this is very simple, and there's a wide range of application. However, the results are pretty much incomplete. You need to have experimental data to complete the empirical correlations. So you can't come up with a solution without those empirical observations and measurements. It doesn't contribute directly to our fundamental understanding of the mechanisms of heat transfer, but it does provide methods for interpreting and correlating experimental data, so it is very useful. The last type is numerical analysis, or computational fluid dynamics. This allows us to obtain approximate solutions to the boundary layer equations. It's very easy to find solutions for a wide range of problems, and these kinds of methods can handle complex boundary conditions very easily. However, it requires a lot of computing power. Now, all of these methods have contributed to our understanding of heat transfer. However, none of them are complete. None of them can tell us the entire story. We have to use all of these methods to get a good picture of heat transfer for convection. So we're going to start by looking at exact solutions. We're going to start with our continuity, momentum, and energy, our fundamental balances. And now we have done this analysis for the velocity boundary layer during fluid mechanics, where you talk about the Blasius solution. He used some mathematics and dimensional analysis to find what we call the similarity variable, eta, and then he also defined the stream function to convert this partial differential equation into an ordinary differential equation, and then solved that numerically to find the velocity profile in the boundary layer. And then once he had this velocity profile, he was able to obtain equations for the boundary layer thickness, the skin friction coefficient, and the drag coefficient. Now we can use a similar process for temperature. Instead of a dimensionless velocity, we define a dimensionless temperature. We assume constant properties, and then come up with this solution. So you see that the axis is a little bit different here. The x-axis here is temperature, and the y-axis is the position. So here we have the surface temperature, and here we have the free stream temperature. And you can see for a Prandtl number of 1, which is this middle line, the solution is identical to the velocity boundary layer solution. However, we have a difference in axes here that changes the direction of this graph. If the Prandtl number is smaller, you can see that the boundary layer for the thermal boundary layer actually extends further into the flow than the velocity boundary layer, because the fluid conducts the energy more easily than it moves the momentum from the wall. And if you have a high Prandtl number, the thermal boundary layer is smaller because it's less able to move energy than it is momentum. Now, as I said, we can then come up with equations for the boundary layer thickness, the Nusselt number, local Nusselt number, and the average Nusselt number, which then gives us the local heat transfer coefficient and the average heat transfer coefficient. And as I said earlier, we assume constant properties. So in order to make that assumption, we have to come up with a good average property. And to do that, we use what we call the film temperature. The film temperature is just the average fluid temperature near the surface. It's the average of the surface temperature and the free stream temperature. Now, this may require the use of iteration. If the surface temperature is not initially known, for instance, you're trying to find the surface temperature for a given heat flux, then you have to make a guess for the film temperature and solve the problem. And if your final solution for the surface temperature gives you a poor match with your assumed film temperature, you may have to iterate the process a couple of times, basically guess and check, to come up with the final solution. We can also look at the Kármán momentum integral approximation. This is one of the approximate methods. It's very useful for turbulent flow. Essentially, we integrate the momentum equation across the boundary layer. And in order to do that, we need to assume what we call a reasonable velocity profile. So we simplify the equation by integrating it, which gives us Kármán's momentum integral equation here. The reasonable velocity profile that we assume should be reasonable for the momentum flux. And from empirical measurements, most people have found that this 1/7 power velocity profile is pretty reasonable. Now, this requires a little bit of engineering judgment because various possibilities exist. But for turbulent flow, the 1/7 power law is very common. It's not reasonable, however, for evaluating the wall shear. So you need to have some correlation for skin friction in turbulent flow in order to complete the force balance for the momentum equation for the shear force. You need to specify the shear force on the wall with some kind of correlation for the skin friction coefficient. The result here is an easy to evaluate equation for the boundary layer thickness. The process is very similar for the energy equation. Here we integrate the energy equation instead of the momentum equation and assume a temperature profile. Now, this assumed temperature profile is usually very similar, for instance, has the same functional form as the assumption for the velocity profile. So for turbulent flow, we might use a 1/7 power profile for the temperature. Again, for turbulent flows, we have to have some kind of assumed correlation for the heat flux, but it gives us an easy-to-solve equation for the thermal boundary layer thickness. So the process is similar. We can also use these momentum heat transfer analogies. We start with the definitions for wall shear and wall heat flux, and we can actually combine these two equations. And when we do that, we end up with an equation relating temperature gradient, heat flux, and wall shear. So we incorporate the definitions of heat transfer coefficient and skin friction coefficient, and we end up with a slightly modified version of the Reynolds analogy. This is called the Colburn analogy, sometimes known as the modified Reynolds analogy. And it actually is pretty useful. It gives us a little bit of a modification to the Reynolds analogy to account for changes in Prandtl number that are different from 1. Now, we need to have a correlation for the skin friction coefficient, so we need to have some model for that. A common model for turbulent flow over a flat plate is given here. It depends on Reynolds number to the 1/5. And it's an empirical correlation. The constants there have been determined empirically. Now, this allows us to recast these equations in terms of the Nusselt number. So now we can move from this Stanton number based correlation through the skin friction coefficient to a Nusselt number correlation depending on Prandtl number and Reynolds number. Now, this neglects the presence of a laminar boundary layer prior to turbulence. Basically, this version assumes that turbulence begins at the very front edge of our flat plate. However, it's also valid when the length of the plate is much, much longer than the critical value. So the Reynolds number is much, much higher than the critical Reynolds number for the transition to turbulence, as we said in the previous presentation, about 10 to the 5th. We can also look at empirical methods. From dimensional analysis, we know that Nusselt number is a function of Reynolds number and Prandtl number. So empirically, we can measure the heat flux, measure the fluid and surface temperatures, and calculate H for a given Reynolds number. And we use the definitions here and just perform a curve fit. So the results here are inferred from experiment, and so we call it empirical. Now, I want to note that no correlation is true. All are basically curve fits that are reasonable for a certain range of conditions. However, if you're using empirical methods, you should expect uncertainties to be as high as 20%. That means you'll want to over-design your system to make sure you don't violate your safety conditions or your design requirements.